The polygons are formed by the ice wedges. The ice wedge is an ice-filled crack. The crack forms during the very cold parts of the winter when the soil in between the cracks is shrinking. And this happens at temperatures below -10 degrees Celsius. These cracks, they stay slightly open until spring snow melt. The water from the snow runs into those cracks and then freezes right there. And then it slightly expands. And the expanding causes the soils to be pushed away. So every year the crack goes roughly in the same place and more water comes in, and so slowly the ice wedge becomes bigger and bigger.
Permafrost, by the most common definition, is kind of geophysical definition. It's based on temperature. So it says any earth material below ground which at or below 0 degrees Celsius for 2 or more years consequently is permafrost.
People are surprised to hear that sometimes, in the high Arctic it even can get up to 20 degrees Celsius. But that heat doesn't travel all the way into the ground. It travels only, on average, half a meter into the ground. That's what we call the active layer. And so the active layer thaws every summer and it refreezes every winter.
We need to know, of course, more, not just temperature, but also how much ice in permafrost, how much carbon is sequestered in permafrost.
So here you see how the pattern of the ice wedges is tied in with the pattern of the surrounding lakes. And in this case, you start losing some of these rims. You could call it thermokarst, because the water that is close to these ice wedges gets warmer because of the sun, and it can erode away the ice wedges and it starts caving in. We call that thermokarst.
So that's a very interesting part of studying permafrost, to study these processes of disintegration of permafrost, which could be very rapid if there is significant amount of ice in the permafrost. If there is not too much ice in permafrost, we can still have some processes of uneven settlement of the surface. We still can have development of thermokarst and thermokarst lakes even, but generally these changes will be much less noticeable than if there is lots of ice in permafrost.
This is a close-up of the white dots, and those are non-sorted circles. I think they are very fascinating features in the tundra because they are created by the interaction between the ecosystem and the physical environment. They kind of work together to enhance each other. So without the plants, there would not be any non-sorted circles, and without the physics of freezing and thawing, there would not be a pattern. The way it works is that you have these barren patches surrounded by vegetation. Every winter when it gets cold, the ground freezes and the vegetation, it slows the freezing down. But the bare patches, they freeze first. And what happens is you get water being attracted by that freezing, because the freezing is kind of like drying. And so the water wants to go into these non-sorted circles. And what happens is they start to rise every winter. And so they rise every winter, and then in summer they collapse again. And this process of rising and collapsing actually prevents the roots from surviving in the center of these features. And so it's the symbiosis of plants growing around it, providing insulation, but they don't want to grow in it because they get damaged from that strong action of frost heave.
Most of carbon stored in the permafrost in form of organic material. It's remnants from vegetation practically. Just counting the area which covered by these kind of sediments and summing them together, it could provide very significant numbers. There is estimates which were made lately of carbon in permafrost, which shows that right now in the upper 3 meters there is more carbon, twice more carbon in frozen state than it is in the atmosphere. So that's pretty big amount. Probably will not happen anytime very soon, but if it will release, the amount of carbon in the atmosphere could be tripled. We see this continuous warming in our coastal sites in permafrost, somehow related to more open ocean during the summertime, because it's increased temperature, but also it increased precipitation. Snow is a very important component for permafrost because it keeps it from cold winter conditions. So if you have more snow, generally permafrost is warmer and much less stable. The degradation of permafrost could happen easier. I think we see already this interaction between more open waters during the summer and degradation of permafrost in the coastal sites. In general, of course, the whole Arctic system will change with changes in ice distribution, and that will affect permafrost as well.
It looks kind of like chocolate milk in a lot of ways, and you can just watch that billowing out into the lake as it mixes with the much clearer lake water. To collect a sample from a permafrost thaw slump such as this, all of this water and ice melts and collects a bunch of the mineral and sediment particulates, and it travels down and it kind of goes out into this mud flat, which is really difficult and treacherous to walk on. Oh boy. Careful! Careful, yeah, it's really treacherous. And it's going to slowly make its way to a little tiny dribbling stream into the lake. So when I collect a sample, I first go to that little stream, which is usually just a trickle. So I have to make a trench to collect enough water from that trickle. I can put in a pH and conductivity probe, measure the temperature, so get some of the physical characteristics that's in this water. And then I have a 8-liter bottle, which I have to first rinse out just to make sure we don't have any residue from anything else. So I pour that in, rinse it, and dump it out. And then when I'm ready to collect, I use a smaller bottle to just collect water and pour it into the larger one. And that's the water we'll actually take home and analyze further in the lab. When you have a thaw slump like this, what happens is somehow permafrost gets exposed to sun and to heat during the summer, and it melts, slumps away, and thus creates a sort of a chain reaction where as it slumps away, it exposes more frozen material that's never seen sunlight or warmth for the last several thousand years, and then that melts away too. And what happens is you get a huge slump forming where more and more material just keeps falling away and falling away. If you can see around here, it can be really a huge feature and can have a drastic effect on whatever is downstream of this material. In addition to that, I also walked over to collect another inlet to the lakes. It's not impacted by a thermokarst failure. It's a clear little stream. It's a deep enough stream that I can just submerge my bottle. Then I fill it with about 8 liters of sample water, again, to take home and filter. So we're really interested in what's happening to the lake as this giant thaw slump continues to grow. There's a very, very huge amount of organic matter that's just been frozen in this permafrost for thousands and thousands of years. And what we see happening in thaw slumps such as this, that carbon, it melts out of the soil and gets released, and then usually ends up in some sort of aquatic system, like a river or a lake. So to understand that, we've got to know everything that's coming into the lake, and what's happening while it's in the lake, and what happens when it leaves the lake. And then how it may affect the lakes that are downstream. This lake flows into another, which flows into another, which eventually flows into the Oxarkoye Creek, which will flow out to the Arctic Ocean. What's really remarkable about these slumps is how quickly they really do grow. In the course of this season alone, this has easily quintupled in size and dumped tons, literally tons of material into this lake behind me.
So that's it. Oh, good. Good we found it. So good we put this flag in. So this is the side, and so the data logger is right here under moss layer. So I try to hide it from mostly from animals, because they like to chew on the wires. Some of the boreholes were established in late 70s, early 80s by a professor who worked here before me. He retired now, Professor Osterkamp. And since then, these boreholes were measured practically every year. So we have continuous records of permafrost temperatures since late 70s.
We use our measurements to validate and calibrate our model, Permafrost Model.
So it's a little bit dirty, but still working, it seems like. So this is a small indicator that's showing that it's blinking, means that it's still logging.
This is a permafrost distribution and temperature of ground. This is a temperature scale. Everything red is above 0 Celsius and blue is below 0.
So that's our 4 sensors attached to the logger through these ports, and it goes into the ground. At surface, at about 50 centimeters, 1 meter, and 1.2 meters. What we are collecting now is 2 years of data, which measured every 1 hour. So 1 hour interval, 2 years, and this is the graph you can see here. So there is surface data, of course, warmer in the summer, cold in the winter, and then subsurface and 1 meter depth is right here.
This permafrost model used as a climate forcing composite ensemble of 5 global climate models, atmospheric models. It was scaled down to 2 by 2 kilometers for Alaska.
So all 2 years of data collected now, and we can work with this data to see what temperature of permafrost is and how vulnerable it is. And actually, I can see it's pretty high temperature, so I guess something on the order of -1 degree Celsius here. So, and it's warm, but it's also very icy, we know, because of the damage of the house.
Picture is kind of modern situation for 2009. It's exactly what we have in comparison with our measurements. It's, I would say, it's pretty realistic picture. I will show you kind of forecast. This is 220, 229. I must say, this is temperature at 2 meters depth. It does not mean permafrost disappeared completely. It's just mean annual temperature and 2 meters depth. Permafrost could be over there, but the table of permafrost just goes down. You can see the north slope is still stable permafrost.
So yeah, Sergey collected data and then started again, and now it's ready for another couple years of collecting data.
I'm out standing at Wolverine Lake. We hiked out here for the first trip, and along that hike we noticed a caribou that just was right near the lake, acting very strange. And when we got closer to it, it really wasn't moving around much, but it seemed to be ducking its head and in a very defensive mode. When we got closer, we saw something small running around it and kind of jumping and nipping at it. I thought for a second it was a fox because it looked kind of lighter colored. But then when we got closer, there's actually a wolverine jumping and nipping at this wounded caribou. It wasn't really bothered by us being there. It seemed to want to keep that caribou in check and make sure we weren't trying to challenge it for its meal, but it came towards us a little bit, checked us out, sniffed us a bit, went back to the caribou, came back towards us, and then eventually ran off, I guess, deciding we weren't worth the trouble or the fight. So we've nicknamed this lake Wolverine Lake because of that. Getting back to the science, when we first came out here, only 3 weeks ago we were out here the first time, this thaw slump was much smaller. The part where I'm standing right now wasn't even thawed yet. So in a typical year, the permafrost only thaws maybe up to 1 meter in most of these places. So from the top of the vegetation, it only ever gets thawed down to about here. But when you have a thaw slump like this, what happens is somehow permafrost gets exposed to sun and to heat during the summer, and it melts, slumps away, and thus creates a sort of a chain reaction where as it slumps away, it exposes more frozen material that's never seen sunlight or warmth for the last several thousand years, and then that melts away too. And what happens is you get a huge slump forming where more and more material just keeps falling away and falling away. Permafrost has been often described as a ticking time bomb of a part of the global carbon cycle. There's a very, very huge amount of organic matter that's just been frozen in this permafrost for thousands and thousands of years. And what we see happening in thaw slumps such as this is that carbon melts out of the soil and gets released. And what we've already seen is that when you expose these molecules to sunlight, they become more available and more readily usable by microbes. And what that means is that microbes can eat that carbon and respire it into CO2, which is of importance because CO2 is a heat-trapping gas that we are interested in understanding how much of the carbon that's now in permafrost is going to eventually end up as CO2.
Well, it is an example of what permafrost does. It melts and it settles your hole whichever way it wants to twist it. Well, I'm Ruth Macchione, and this is my home. And I live in outskirts of Fairbanks, Alaska.
I'm Vladimir Romanovsky, and I'm a professor in geophysics at the Geophysical Institute of the University of Alaska, Fairbanks. Also, I'm professor at the Department of Geology and Geophysics.
Couldn't hardly live in it no more. That's why that new house came up. I had everything blocked up, you know, to level, like your table, your refrigerator, your stove, all that. I had to have the bathroom redone downstairs. And, yeah, a lot of work.
To completely thaw even warm permafrost like it is here in Fairbanks, which is -1 or warmer, it takes hundreds of years. And good example is exactly this site, where permafrost started to thaw because of disturbance, because it was forest, it was removed, and now it's agricultural kind of field. And it happened in a very late 30s, early 40s. And so it's how many years? 70 years now. Yeah, it will be 55 next year, the house. Yeah. 70 years of thawing of permafrost developed 11 meters of non-frozen layer. From 11 to about 40 meters, it's still permafrost there.
This house is solid. Why is that?
Why is that? Because they did a different foundation, and plus, before they built, they drilled down to see where the frost line was. On the back side, the two corners back there was 37 feet down before they hit frost. And up here it was 27, the front.
So we did a little bit of drilling when Peter decided to build there. Well, we found that it's actually in the forest, permafrost is pretty shallow. It's maybe 6 feet only, but in the opening it's already down there and it's thawing. So, and well, it probably will be stable if it will be kept like this. But what I said, that just try to not get any water under the building, because that could make big damage there. If it's open during the winter, of course you need more heat to warm up house, but it keeps ground more stable.
So by allowing it to be colder, actually,
It's more stable, yeah.
But it'll freeze. It'll push up when it freezes. It'll push up, because I could hear the door, you know, it gets tight and shut on the outside door especially. And then when it thaws, it settles back down to where it was.
If one corner will be, say, moving not the same rate as other corners, you can jack it and you level it. Now new houses built on permafrost this way.
See a lot of them over this way. They're still standing nice and straight over on Kitty Lake and that.
Yeah. So that's new way to design and build.
There's always something changing.
Hopefully it will work for longer.
Your lifetime anyway.
Yeah.
Let someone else deal with it.
The plan was to put it underground, all the way from Prudhoe Bay to Valdez, because it was some company from Texas, and how they do in Texas, they decided they will do it here as well. Unfortunately, these plans came for review to U.S. Geological Survey, and Art Luckenbrook, who is one of the fathers of permafrost research in the United States, he wrote very short notice, maybe 5 pages, saying that it will be disaster. And it was fortunate that it happened, because otherwise it would be. We will have huge problems with this pipeline. So of course, after they reconsider and put this pipe above and put some, not just piles, but thermopiles, it's actually some small refrigerators there, which the pipe is sitting on. They're refrigerating ground below the pipe. Because of that, we don't have big major problems so far with the pipeline. But even with those measures, which of course double price or even more of the pipeline, because it's much more expensive to build it this way, it make it stable. But even with all this very good engineering solution, right now at some locations, They keep permafrost only around these thermopiles. It's already gone from the area around it. Because of construction itself, because of climate warming, in some locations they keep some bulbs of frozen ground just under the pipeline. And they're not sure how big this bulb should be to continue to support the pipeline. So there is some questions, even with this very good engineering solution. With further warming, it could be not enough. To completely thaw permafrost, even in interior Alaska, it will take hundreds and hundreds of years. However, the most of the organic material and carbon sequestered in the upper part of permafrost, and the most amount of ice is also in the upper part of permafrost. So even if we have some 3 meters of thaw, which we have after good forest fire, permafrost thaws down to 3 or 4 meters. Even if it's just 3 or 4 meters, it's already a huge impact on infrastructure and on ecosystem and on carbon cycle. So we don't need to wait when all permafrost will be gone to have effect. Effect will happen actually immediately after permafrost start to degrade. On one side, permafrost will not disappear anytime soon, so our job is pretty secure. Yeah. On another side, any active degradation of permafrost, even from the very beginning, will have impacts.